inviting Professor Art McDonald, who will speak about solar neutrinos, flavor change, solve the long-standing problem.
Well, I'd also like to thank the organizers for the opportunity to speak at this conference, but I'd like to thank them even more for the opportunity to participate in this wonderful set of discussions and presentations on the history of neutrinos. I've learned a lot and got some interesting perspective from it, so thank you very much for the opportunity to be here. So I'm going to start by talking about the Sudbury Neutrino Observatory, but I'm also going to combine that with discussions that build on the great talk that Till Kirsten gave earlier on of the other pioneering experiments that addressed solar neutrinos, and I'm going to carry on with the experiments that have occurred since 2001, 2002 that have continued to give us information about neutrinos and also about the sun. But let me start with the fact that, let's see if this works. Yeah, we owe a lot to the pioneers in this field, and certainly Ray Davis and John McCall were pioneers. I had the advantage of being a graduate student at Caltech in the late, from 65 to 69 in Willie Fowler's lab, Kellogg lab, and Davis visited in the summer. John was a junior faculty at that time, and it was a fascinating time to be there as measurements were being made of chlorine cross-sections and discussions were going on about the experiment, and I remember the great discussions after very few neutrinos compared to calculations were observed. But I'd also like to pay tribute to Bruno Pontecorvo and Gribov for both the original suggestion of flavor change as a possible explanation for properties of neutrinos, but also as a possible explanation for what was happening in the solar neutrinos. Now, these measurements of Davis, of course, continued through many years, showing a factor of 3 or so discrepancy between calculations and observations. And in 1984, Herb Chen, who was a fantastic scientist from University of California at Irvine, contacted, I think it was Cliff Hargrove in Canada, with whom he'd worked before using deuterium at Los Alamos, and said, do you think there's any chance we could get 4,000 tons of heavy water on loan? That would have been $1.2 billion worth of heavy water at the time. And so Cliff contacted several people at Chalk River and other places, including actually Jeff Hanna, who was a co-author with Bruno Pontecorvo on that proportional counter measurement of neutrino mass. And the answer came back, well, probably not 4,000, but maybe 1,000, which was very good news to about 16 of us who had come together by this time for discussions with Herb about the possibility for this experiment. George Ewan, wrong button. George Ewan had been exploring underground sites, and he had a commitment from International Nickel for a 2-kilometer deep site in their mine for this experiment. And so we spent a number of years working on the development of a proposal. This actually shows a Snow collaboration, almost all of us, in 1986. And unfortunately, this picture was taken within a year of Herb's death. He was just beginning to show the difficulties of leukemia when he was at this meeting in the fall of 1986. He and George Ewan were the original spokespersons in Canada for the project, and David Sinclair brought the UK into the project in 1985. I was working on the project from Princeton University, and when Herb passed away in 1987, I took over as the US director and then moved back to Canada, where I'm from originally, in 1989 to take over at Queen's University from George Ewan, who was about to retire. So it was a small group in the first place, we spent a lot of time between 1986 and 1990 developing a proposal and getting good peer review, which was just the start. Getting money of the scale we needed, around $70 million to do the project, was non-trivial in Canada. About 25% ended up coming from the US and 5% from the UK. But the idea that Herb put forward, in fact, in a paper that he wrote at the time, was that you have rather unique properties if you use deuterium to address solar neutrinos. There was the solar neutrino problem, as it had gotten to be known, of a discrepancy between measurements and theory. You have one reaction on deuterium, a reaction that's very specific to electron neutrinos, in which you produce a fast-moving electron in the detector, which you're able to observe, and another reaction, which you see here, in which you basically just produce a free neutron. And we actually designed the experiment with 3 different ways to detect that. And by comparing those 2 reactions, you're able to tell if electron neutrinos have changed their type without recourse to the measurements, or rather the calculations of the boron-8 neutrinos produced in the sun, and that was the essence of what we were trying to do. And we knew we had a good experiment which could tell us about the properties of possible oscillations of neutrinos, but also through this reaction could tell us about the absolute flux of boron-8 neutrinos, whether or not oscillations were taking place, if we could only do it. And that was a problem, because any reaction that gives you a free neutron in the detector was a background to what we were trying to do for that second reaction. And so we had to work very hard to control radioactivity throughout the construction, selection of materials, control of dust. We ended up with water in the middle that had less than 1 radioactive decay per day per ton of water from the uranium and thorium chains. So it was very stringent requirements. Eventually we were able to do it. We were also able to measure that radioactivity and characterize the background. But when we started out, that was the real challenge. Now, in addition to that, of course, in water, and this is what Super K used very effectively to make beautiful measurements of solar neutrinos, you have the elastic scattering reaction, which really is sensitive to all neutrino types, but the electron neutrino sensitivity is enhanced by about a factor of 6 compared to the other neutrino types. So you've got about a 15% neutral current sensitivity, a significantly lower rate, but it does have a significant advantage in terms of directionality. It points essentially directly away from the sun and can be extracted in that way. This reaction actually is rather nice in that it gives you energies of electrons that essentially mimic the incoming electron neutrino energy, and therefore you can get a spectrum from that give you an indication of the neutrino spectrum coming from the sun. You can get that from the elastic scattering, but it's somewhat washed out in comparison. So to detect neutrons, we use 3 different techniques in 3 different phases of the project that you can see listed there. At the beginning, we had pure heavy water. We looked for evidence for 6 MeV gamma rays produced when the neutron is captured in deuterium itself. Efficiency for that capture was on the order of 14%. In the second phase, we put in a pinch of salt and increased that to 40%, but also because the pattern of events as observed in the detector for multiple gamma emission compared to a Cherenkov single event for the electron neutrino events, we were able to separate statistically neutral current and charge current reactions and get a measure directly of the numbers of total number of neutrinos coming from the sun. And then finally, for the last phase of the project, we used about 400 meters of proportional counters that were quite remarkable in their not only their ability to give us neutron signals, but also in the fact that they didn't add significantly to that 1 radioactive decay per day per ton of water. They were very carefully made by a team led by Hamish Robertson. So this is what the detector looks like. It's been exhibited many times. We were very fortunate to be 2 kilometers deep in an active nickel mine. They're still running it to take thousands of tons of ore a day. We had the heavy water in a central acrylic sphere, looked at by about 10,000 phototubes in a chamber that was itself waterproof and radon-proof. It was done with multi-layers, so we suppressed radon about a factor of 10 to the 5th coming out of the surrounding rock. During construction, we had a principle of once we had the central chamber coated and ready to go clean, that everyone took a shower and changed to lint-free clothing. You can't quite see it here, but everybody has on lint-free clothing, and we constructed the whole thing, and we estimated from measurements by the time we were finished, we had less than a microgram per square centimeter, which means about less than a total gram of dust on the 1 million parts or so of the detector. There was a major effort to construct the acrylic sphere, which actually took us about a year and a half extra because we had to fabricate it from 120 pieces bonded together in place, and it took us as long to do the roughly 5 meters that had small bubbles in that in the total length, which was almost a kilometer of bonds, as it did to do the entire rest of the sphere. So that was certainly a holdup in terms of being able to get on with the project. Here you see the water purification system, which actually was David Sinclair's contribution. He led that effort, and we accomplished what we needed with that. So these are schematics of what the data looked like, just to show you how we approached it in the various early phases of the project. What you see here is a major background wall that cuts in around 50 phototube hits at about 9 hits per MeV. This is the charge current reaction, and this is the neutral current reaction as evidenced by the capture of gamma rays in deuterium, about 6 million electron volts. And this is the elastic scattering reaction. And this is what you see if, in fact, you have a suppression of the charge current by a factor of 3, as would be what you would observe if, in fact, Ray Davis's results were indications of neutrino flavor transformation. So the first analysis we made of the data was published in 2001, and it was with a threshold here because we really had to worry about being sure we had all that radioactive background that underlay those neutron events tightly controlled. But there we benefited greatly from the great work that had been done by the Super Kamiokande collaboration up to that point. They had a very accurate measure of the total elastic scattering cross-section, although they had not been able to observe something that was independent of neutrino flux calculations from the sun, which would have been either a distortion of the spectrum or a day-night asymmetry, which turned out in this case to be very small. It was eventually measured by Super K at I think 2.5% level, something like that. It just didn't, it happened at that time. They didn't have the statistical accuracy to do it. On the other hand, the measurements that they had made of the total flux were very accurate. We were able to measure the charge current reaction. And remember, this has about a 15% sensitivity to neutral current. And it turned out that if you took the difference between these two, then that was representative of a neutral current flux, which gave us a 3.3 sigma result for neutrinos changing their flavor. Here you see things plotted on a plot which has mu tau flux on this axis and mu tau neutrino flux on this axis and electron neutrino on this axis. And you can see how the various sensitivities, there's Super K, there's charge current in snow, translated into a finite mu tau flux at this point. Now, the next analysis we did, which we published early in 2002, was a full analysis where now we were satisfied that we had characterized the radioactive background, could control it with an uncertainty of about 10% through restriction and also measurement of it. And that resulted in a measurement which you see here in terms of the full fit of the data, which we did as a function of energy, of radius, and of angle to the sun. You can see the elastic scattering here, as you saw typically in from super K. This is the charge current reaction, which did have some solar angle dependence, and neutral current plus neutrons, which we had restricted. And that fit enabled us to measure charge current, neutral current reaction, but we expressed it in terms of mu tau flux and electron neutrino flux. And you can see that there was a greater than 5 sigma conformation of flavor change from the mu tau figures. Again, this is okay, so now we move to the next phase, and by the next phase, when we put the salt in, we had enhanced our sensitivity. We also had the ability to look on a statistical basis separately at charge current and neutral current. By the way, I should say, I missed one. This was done, I mean, the confirmation of flavor change was done as a hypothesis test of no flavor change by assuming there was no distortion and looking for whether we saw anything that was at discrepancy with that assumption, and the answer was there was a 5.3 sigma distortion. Yeah, the intermediate thing I wanted to show you, and there was a lot of discussion of simulation of experiments and convincing funding agencies and so on earlier in this conference. This is actually what we submitted in 1987 as a part of our review process of what we might expect to see in the pure D2O phase and in the sodium chloride phase of the project. And you can see the projected background here. You can see charge current dominating, a small component of the neutral current. This is the data, and this is the fit that we obtained. And then you put salt in, and what you do is boost the sensitivity for the neutral current by a factor of 3 or so, and you have the opposite where the neutral current is the largest and the charge current is shown here. And really, I'm still impressed by the quality of the simulations that my collaborators made at the time that we were putting forward the proposal as things panned out. This is after we put the salt in, and we had the added advantage of independently determining the neutral current part of the fluxes, and interesting that this number was also very close to the calculations that were made at the time, and the flavor change was indicated by this point at about 7 sigma or so. Here's the ratio of charge current to neutral current, which is almost directly proportional to sine squared theta 1, 2, and it's clear that only about a third of the electron neutrinos remain. In the third phase of the project, we installed about 400 meters of these low background neutron counters installed with a remotely controlled submarine that could only be operated by somebody under 23 or so. Nobody else had the manual dexterity to do it, and we tried, but we'd only allowed young people to do it. And if you had a chance of putting a submarine in your $300 million worth of heavy water, what color would you choose? Well, of course, we chose a bright yellow submarine. Turns out that paint was so radioactive we had to strip it all off, and so there's the actual submarine that we ended up using. But it worked very well, and we had great data from that phase of the project as well, including the ability to do pulse shape discrimination on the pulses that we got, where we had, I mean, typically what you're looking at is neutron capturing on helium-3 and going to a tritium and a proton. And so with a neutron source, we could produce what that should look like. We had a few of the detectors that just gave you the typical background, and here's the fit for those two components to the to the actual data from them. And from that, we got, by combining all three phases, our final result, both for the charge current to neutral current ratio and also the total flux. And so here's the 273 historic authors on our papers, and I give a Nobel Prize to one person, but those are the people that actually did the work on this project. And actually, since we're talking history of the neutrinos, it's kind of interesting from this field, or any field of physics, it's interesting from a sociological point of view. We did a summary when we came back, when we finished running. After about 10 years, we asked where those people ended up. About 25% of them are university professors, but 35% of them are women. The other 75% either own their own companies, or are directors of technology, or are actively involved in research and development in industry. They're advisors to government. They work in finance. 75% of them are out there doing other things. We attracted them in the first place by fundamental science, but we're finding, in fact, that we're doing a great process of educating people in evidence-based decision-making, and that's of value to society in general. So let me include the other solar neutrino measurements, which were summarized by Till very well. By the time we were finished, we had our neutral current results matching theory. The other experiments were low because of neutrino oscillations. And the analysis, as we just heard very eloquently from Alexei, was due to the adiabatic effect in the sun. From it, we learned that mass 2 is greater than mass 1. Delta M squared was defined, and the mixing parameter was defined. Very shortly later, end of 2002, the Camland collaboration published absolutely beautiful data with reactor antineutrinos. And what's fascinating, of course, is that their results, which also, of course, depended on the 1-2 parameters, matched the large mixing angle region obtained from the solar data, giving strong confirmation of what was happening, but also giving a very nice definition of the delta M squared, where the accuracy in the Camland results resides. Now, to summarize where we are today, I'm going to run through a few talks. You can't see the bottom of this slide, unfortunately. I tried to leave it on. It was a very nice conference on solar neutrinos in Dresden this summer. These are slides from Yurichiro Suzuki. You can see that they now have very nice measurements on solar neutrinos, providing significant constraints. They have a finite result, 2.6 sigma, for day-night effects of matter interaction in the Earth. They're looking very hard at the upturn or possible upturn in order to match what you see at the lower energies, but do not yet observe such an upturn. And Borexino, a really beautiful experiment done with ultra-pure liquid scintillator at Gran Sasso. It has had a number of phases, all of them contributing significantly to our understanding of solar neutrinos. In the first phase, we had a nice result from beryllium-7 and PEP, first observation, further numbers on the boron-8. In the second phase, they actually made measurements of PP. They also made measurements of seasonal variations of beryllium-7, and simultaneously observed all three of these and improved the numbers on boron-8, as well as geoneutrinos, neutrino magnetic moment, and of course, non-standard interactions are a continuing study for solar neutrinos. They're now in a campaign to do a CNO measurement, and with SOX not being technically feasible, it gives them an opportunity to proceed with some measurements of that. This is what you're looking at in terms of the data from Borexino, and you can see PP is observable down here. Beryllium-7 is a shoulder here. PEP is discernible after you suppress the carbon-11 background that you get by some nice coincidence measurements. But the big problem with CNO is the interference between the CNO itself, which is this red line, and bismuth 210, which is this green line, that's very difficult to control and to define how substantial it is. However, they are now able to we can use this data to make comparisons of solar models, and there appears to be at least some preference for high metallicity in terms of the fits to this set of data. I think ongoing, what's going to resolve things in that question is actually a measurement of CNO, and that was addressed by Professor Valenti in Dresden in terms of the fact that in order to try to improve measurements to get to the CNO, you want to reduce the carbon-11 and, of course, control the bismuth in order to get at CNO. SNO Plus, which is has the main objective of doing neutrinos double beta decay with tellurium, has been running for a year with light water and is about to put scintillator in. This is the data for boron-8 neutrinos that you see now in SNO when you don't have any contributions from deuterium in this vicinity. And there's a well-defined elastic scattering peak for high energy boron-8 above 5.5 MeV. There's essentially no background in the detector. These are projections for, and I have to say, actually optimistic projections, because we really don't know how much bismuth 210 we're going to have in the detector until we turn it on. And we're just about to put scintillator in starting this month, and it'll be interesting to see. But you can see that the projections indicate that in our depth, carbon-11 will be here rather than up here, and so it'll be quite interesting to see what gets observed, and we're going to learn a lot from what Boroxino has done in terms of dealing with bismuth 210 and the associated polonium information, which you can measure rather well from this peak here. We would hope to have measurements on this order in a 6-month period if the background works out, and then at that point we should be ready with our tellurium purification to install the tellurium. So finally, I think nature has been kind to us in terms of some of the discussions we had earlier of how a number of parameters and different things have come together. Let me add one thing. I think this field, particularly I'm conscious of with solar neutrinos, has benefited fantastically from the collaboration between theory and experiment. For example, Alexei's wonderful work on the MSW meant that when it came to results from SNO and results from CamLand happening essentially within the same year, you had the ability to translate between these two rather different experimental situations with understanding. But in addition to that, all the work that was done on global fits, attempting to understand from all of the experiments that Till mentioned that were done so well prior to this for guidance, it was great. And I think that's characteristic of this field. We've had theoretical perspectives given at timely points, and that's been very helpful for the experimentalists as well. So I'll just go on to say that there will be more information in the future, and many of the large-scale detectors being built for other things will have supernova, will have solar capabilities, supernova as well for that matter, and it'll be interesting to see what comes out of those. So stay tuned to this field. It's certainly going to continue to contribute. Thank you very much.
Thanks, Adam Bernstein, Lawrence Livermore National Lab. Thanks for your very nice talk. Just kind of a question about backgrounds, which is this wall at roughly 5 MeV in your threshold. And then if I just sort of naively think of backgrounds in low background detectors, I tend to think that the ambient radiation ends at about 3 MeV. And I'm just wondering, I think you understand your backgrounds pretty well. Can you explain what is sort of intruding in that regime between 3 and 5 MeV that causes the background to be so high?
Well, it's largely energy resolution, creating tails of what is a really substantial background from the things you're talking about. It's uranium and thorium, and it's predominantly coming from outside of the detector. If you look at things as a function of in this case, R cube, a function of volume, therefore, where this is the acrylic sphere at 1. There's a certain projection of the external background inside the region of interest, and we picked our fiducial volume based on that, but there's still a little bit coming in here. But really, it's the tails caused by energy resolution.
Thank you.
I'd like to stir up the discussion about the contribution of theory to the neutrino business again.
Very hard
But
to
there's-
imagine you trying to stir up a discussion, John. You turned over a new leaf or something?
Yes, right. But look, the difference is that our phenomenologist friends have been wonderful and participants in all of this, partners in it. Where has been the problem is the lack of any fundamental theory, any guidance about where the oscillation should be, neutrino masses, blah, blah, blah. It's been groping about in the dark for us in the neutrino field all the way along. Everything that we found was not anticipated. There were mechanisms that were anticipated, but our really most basic problem is that there is no grand unified theory to point us in the right direction. We play with things like the seesaw mechanism, which is really just a mechanism, not a fundamental process. Anyway.
Excuse me, John, but you're saying you want them to solve it all before we do our measurements. Is
I
that what you're
want
saying?
them, yes, I would like to have
Just wanted
more
to get
things
it
to
clear.
shoot at, like a real prediction of proton decay lifetime, for example.
Comments? No question, no comments? So, we thank the speaker again.